Okay, so I think you can sit if you want to, or do you want to stay?
I stand. It's fine.
Okay. So we will be introducing life cycle assessments to you, and we'll be doing that on a practical example. And so basically, we thought it would be a nice way of introducing this topic instead of having like this big theoretical block and then kind of showing you the example in the end to kind of move along with the example to kind of make it more easy to grasp in a way. But that also means some things will maybe be explained a bit later in the lecture, and some things might be unclear to you also. If that's the case, please ask away immediately. Feel free to ask. Yeah. And so what we're going to do is we're going to introduce the lifecycle assessment of the Fairphone 5 to you, which is a lifecycle assessment that we conducted. We'll show you how we did it, what the results were, and how you can actually read LCA results. And then we'll also give you a brief intro into ecodesign. And maybe shortly before I get into the block of the lecture, basically in your exercise tomorrow, you will be working on this example that we show you today. So you don't have to do a life cycle assessment yourself, but this is going to be the baseline. So maybe that can be a small motivation to kind of pay attention to what we're telling you. Yeah, so before we get started, let's set the baseline and talk about what an LCA actually is. Who of you knows what a life cycle assessment is? Ooh, okay, there's hands. Yeah, maybe you.
Right, okay, it's about the inputs and outputs of materials, emissions, and other stuff during the whole life cycle of the product. And from this, you try to calculate the environmental impact of the product, of its manufacturing process, of its use space, and also of the recycling phase. Finished. Thank you.
Ah, okay, yeah, sorry, there will be some questions. But yeah, very nice. That was already a very good explanation of life cycle assessments, so I couldn't have said it better myself. So basically, we look at the impacts throughout the whole life cycle, and I'm already showing you this life cycle here because this is the life cycle that we usually work with for a product. So it's all the way from extracting the raw materials from the earth or from nature through the whole life cycle of a product all the way until disposal. And this is what we're going to talk about today on the example of the Fairphone. And so I also wanted to take a second to explain to you what a Fairphone is in case you don't know. So you can actually see it on the left-hand side here. And Fairphone, confusingly enough, is a company actually that produces a smartphone that is also called Fairphone. And you can see the evolution of their models on the left-hand side. So they've been doing that for a little over 12 years. And we have been working closely with them on conducting LCAs for their smartphones right from the beginning. And they kind of have this mission of promoting more sustainable electronics and fairer working conditions for their workers, which is where the name comes from. And I want to take a second to show you the core principles they have, because I think it's an interesting example of how these kind of mission statements can translate into actual LCA questions and goals. And so they work with more ethical supply chains. They want to make working safer for their workers. They want to pay fair wages, which is something that you would see more maybe during, like, when working with a social LCA, which also exists. But we're focusing on these environmental impacts. And here, maybe something that's interesting from their core principles is that durability and repairability are also one of their core principles. So having a modular design that's easy to repair and upgrade, and trying to extend the product lifetime as much as possible while still keeping functionality. They want to have transparent communication along their supply chains and manufacturing processes, also to the consumers, and they want to minimize the environmental impact along the whole product life cycle, which is obviously also where this LCA classically comes in. And so questions that we typically answer with an LCA are being shown here, and I kind of separated them into questions that you will see in a second that are always the same and questions that are a bit unique to this LCA of the Fairphone 5. And so typical questions that we have, as you can maybe imagine, is what is the environmental impact of a product throughout the whole life cycle? So in this case, the Fairphone 5, but also what are the main drivers of this impact? So the question there is really that we're also trying to answer is which components, which life cycle stages, which materials really drive this impact, with kind of the idea of, okay, especially in this case, because we're continuously working with Fairphone, the idea of maybe changing this in the next iteration of the smartphone. And then there is also the question that we answered in this LCA of how does repairability affect the environmental impact, and what additional manufacturing efforts do we have to take for modularity. So Fairphone really is also a modular phone that you can kind of take apart and, for example, exchange the camera quite easily. And there, I think there's an interesting question that comes really with all types of environmental assessments quite quickly, because here I put down as research question, is repair ecologically beneficial and under which conditions? And usually you will find very few things that are under all conditions measured against all categories really the more beneficial option. But oftentimes it's like there are certain conditions under which it's more beneficial, but if you use it differently, it might not be more beneficial. So maybe there's a higher production impact for repairability, so you also have to use the phone a bit longer. This is a small spoiler maybe for later on, or for tomorrow for the exercise. Yeah, and then we also assessed the environmental impacts or benefits of using recycled materials as input materials. And we thought about how we can measure this more efficiently and effectively. And then we also assessed the impact of using renewable energies instead of fossil fuels for the manufacturing processes of different components. Yeah. And then we get into how the LCA was conducted. But before we do that, I'm gonna show you a slide that is a bit overwhelming maybe, but really you don't need to look at this in detail. What I really wanted to show you with this is just that LCA is not just one method. There is a lot of different standards. There is different subcategories. There is different specific product rules for individual products. And so there's also, for example, the product environmental footprint, which is kind of the EU standard for life cycle assessments. And so it always depends a bit on the standard, what specific requirements you have to fulfill, for example. But there is this core standard that is the ISO 14040 and 44. And this is I'm going to be using to kind of explain to you life cycle assessments today. On one hand, because we conducted it with this standard, and on the other hand, because I think it's a nice way of showing this, because in the end, even though they do have specific methods here, obviously the basic way this functions is the same. Yeah, and then, okay, we've seen the product now. This is what life cycle assessment results look like, but now the question really is, how do we actually get from this on the one hand to the other hand? And the basic way to do that is through modeling it and through kind of breaking it down into blocks. And I brought to you an example of a different life cycle assessment. So this is a schematic presentation of a life cycle assessment of a laptop that we did. And here, can I point? Well, I can point. Okay. Basically, when I show life cycle assessments to people who have not worked with them before, a lot of times what they say is, oh, hey, it is really just like a flow chart, kind of. And I think that's a very neat and convenient way to think about life cycle assessment. So you have input flows, you have output flows, and you have kind of, so for example, this is the whole laptop that was manufactured, and then you have all the different components. So keyboard, display, storage. There is different cover parts going into the cover, different different materials going into this. And then this kind of moves through the whole life cycle all the way to the disposal. And really, it is just a quite complex flow chart in a way. Yeah, and so the way the ISO standard defines this, there's 4 steps to this, and we'll be moving through all of them one by one. So goal and scope, lifecycle inventory, impact assessment and interpretation, and we'll be showing you the details of that in a second. And so we're starting with the goal and scope because it does make a lot of sense to think about what you're actually trying to assess before you start doing it. And there's really 3 kind of keywords that describe this. So one is the goal, the functional unit, and the system boundaries. And we'll be defining them for this lifecycle assessment that we're gonna do or that we did. So for the goal, we already talked about this before. So this is the environmental assessment of the Fairphone 5. We want to see the environmental hotspots and main drivers. We want to assess what impact recycled materials have, renewable energies, and also assess the effect of repairs. And for the functional unit, this is a very important word in terms of life cycle assessments. So I want to take a second to introduce it to you. So basically, an issue that we have a lot of times is especially when we assess multifunctional products, so we cannot really just compare the product because different products so they're doing slightly different things. They're able to do slightly different things. And so to make the comparison more fair, we compare functional units rather than products. And I like this example of a wall paint to kind of show what this means. So really, for example, if we would do an LCA of painting a wall, we wouldn't assess the amount of paint in the first place, but we'd rather compare how much paint you need to kind of paint, for example, 1 square meter of wall, because depending on the quality of the paint, this might be vastly different amounts. And so 1 square meter of wall would be our functional unit here. So this is kind of the reference unit. And then there's also something that's called reference flow, which is how much of the product you're comparing do you need to fulfill this. So basically you might need 1 liter of paint A, but you'd need 1.5 liters of paint B. So that would actually be the amount of product that you're comparing to each other. And now that I've so neatly explained this to you, I'm gonna slightly break this pattern by saying the functional unit for our LCA is manufacturing and use of the Fairphone 5 and accessories by consumers across 3 years. And so there is some researchers who say that this is not an accurate way of defining a functional unit. We still think it is, because basically you kind of define, for example, you define all the important technical parameters, so the storage size, the display size, all these things. We define the use phase through this, so it's not in the sentence, but we do define it along the lifecycle assessment. And so actually I think this is a very neat way of expressing a lot of things in just 1 sentence. And so basically the Fairphone and its accessories means a smartphone, protective case, the screen protector, also some earbuds that come with it, and a bit of cable. And so that's what we're really trying to assess. Yeah. Because this is the most common unit being used in lifecycle assessments of smartphones. So Apple, for example, also assesses theirs for 3 years, but usually for Fairphone, we have also done assessments for longer time. So actually the lifetime they aim for, I think, is 10 years now, but they're more around 5 to 8, well, obviously depending on the consumer. But this is really just for comparability's sake. You shouldn't compare different life cycle assessments just like really right next to each other, but it does make it easier to read the results in comparison. Yeah, and so second to last thing I want to introduce to you before we get into the details of the Fairphone 5 is the system boundaries. And so we kind of talked about this before, but the theoretical concept underlying this is that if we do a full LCA, we go from ecosphere to ecosphere. So we take something from nature, we work through it with our technology and human as humans, and then we kind of put it back to nature. And this is the ideal way how we would conduct life cycle assessments. Oftentimes in reality, this is kind of limited by workload and data availability. So we sometimes scope down, our scope is a bit more narrow because we might not have the capacity to do like a full-on assessment, or we think we know the hotspots already and just focus on them. For the Fairphone 5, we did kind of this full LCA, so we did cradle to grave, which is this analogy to human life that life cycle practitioners really like. I always think it's a bit strange because we talk about these products, but basically we go from raw materials to disposal, and through that all these different steps of working with the product. And then the last thing I want to introduce to you is impact categories. And this is actually something super important, but also the name is pretty descriptive. So impact categories really, we use them to calculate the environmental impact. And environmental impact is a super generic word, but obviously there's many different environmental impacts that you can have, and we kind of categorize them into different groups. And this is really what an impact category is. It's a classification of substances and impacts depending, like based on one specific impact. So the most common one that you might also have heard of is the global warming potential. Which is always shown in kilogram CO2 equivalents. So this is how much substances or a product in this case might contribute to the potential global warming. Then we have the resource depletion or abiotic depletion potential, which is always shown in antimony equivalents. And this is basically a measure for the potential future scarcity of resources that might take a long time to regenerate or that are not renewable at all, like fossil fuels and minerals. And then we also have many other impact categories. They differ a bit, but there's really in total with different measuring parameters, there's like well over 20. And then one other one that is maybe easy to grasp, but the unit is not, is ecotoxicity or human toxicity. And the way we usually do this is we have a substance and there is something that's called a contribution factor for this substance. So I'm going to go right to the example on the side. I chose methane. And so, for example, for global warming potential, the contribution factor of methane is 25. So 1 kilogram of methane has 25 times the potential impact on global warming over a period of 100 years than CO2. And CO2 in this case is the reference one that we kind of display all of this in. And then so to get the total environmental impact, we just kind of sum it up. So this is really just a numbers game of sums. So if we had, like in our life cycle, 1 kilogram of methane and 1 kilogram of CO2, our total CO2 equivalent for global warming potential would be 26 kilogram. So it's really the underlying maths is really quite simple. There is obviously more complex impact categories as well. And to summarize what we want to do with the Fairphone 5, so we did an LCA that is ISO compliant. The functional unit is the production and use of the Fairphone 5 and accessories by consumers over 3 years. The impact categories we chose in agreement with Fairphone, so that's either something that is defined by your standard or you agree on it beforehand with whoever's contracting your LCA, or if you do it yourself, you're free to choose. So we had climate change or global warming potential. We had this abiotic resource consumption, ecotoxicity, eutrophication, which is kind of how enriched the enrichment of a water body with nutrients, so usually like nitrogen or phosphorus, and that can lead to like algae growth, oxygen depletion. Then we have land use change, which is stuff like deforestation, for example. So how much is like a land ecosystem impacted by this? And then we have water consumption, which is pretty straightforward. And as I said, we go through the whole life cycle, and then we from cradle to grave, and then we also assess the recycled materials, renewable energies, repair, and the lifespan of the smartphone, which is this question of how does the impact differ if you use the smartphone for a longer time. Yeah. And so for step 2, which is called the life cycle inventory, that is basically just a long list of different materials and components and flows that go into this product. And there's 3 different parts that might be interesting. So the one is data collection, which is what we usually spend a lot of time on. And then we kind of collect, like in this case, as it is a product, we have these different components, and then we kind of assign material and energy flows to it, that are underlying through these components. And then we have a question of allocation, which is if you, for example, have a factory that produces many different things, how much of that impact do you have to allocate to the product? And this is usually in a case as complex as the smartphone, we ask ourselves these questions for maybe the assembly energy, but the underlying processes, this is really covered by the databases we use, so we don't concern ourselves with that too much. But for the data collection, this is usually what we get from the manufacturers when we are actually, so if the task is, hey, conduct an LCA of the smartphone, this is what we get. This is called a bill of materials. It's basically just a long Excel, in our case, it's an Excel table of different components and parts that are in the smartphone. But the issue with that is they're often not clear enough, they're often not detailed enough, they've often been, like a lot of times we get, this is the list that the sales department, for example, usually uses. So they might have like 2 entries for one component because they have different suppliers. So there's usually almost always something that we need to change to make this workable for us. And also, even though it is called bill of materials, usually they don't contain the materials that are actually in these components, which are really interesting to us, actually. So we always need to work on this a little. And so what would you do if you had a product and you have this list and you know this is not enough? What would you try to do to yeah.
So I know that bill of materials is also used, it is used to partner with production operations. And so it's, as you said, there are no material, but that means let's say plastic cover for the phone or something like that. So we will, in my opinion, we should dive down and let's see how much plastic or how much metals are used.
So how would you do that?
By weighing or by looking at suppliers, how much they did in their bill of material. So I'm maybe going back and back to whether possible finding the basic material.
Yeah.
I mean, in the best case, the supplier already made the life cycle assessment. If we could cooperate in that way, and otherwise the approximations that are based on.
Yeah, so that would be the ideal case, obviously. But actually, unfortunately, we have had some experiences where we had supplier LCAs and they actually weren't accurate. But I mean, I think it's also because this is really starting up, and I think in a couple of years we will have more supplier LCAs and they will be more accurate, but as it happens, this is just starting out and there's always some issues in the starting phase, but that would be very nice. Also getting the data from the suppliers, we have that sometimes, that's also quite nice. So there's also something called a declaration of full material declaration where we have these materials. But you kind of implicitly also said what we usually do to familiarize ourselves with the product. We take it apart. And so, to be honest, this is my personal favorite part of doing these LCAs because we get to break the products. We only do it with one product. There's always people going, oh, hey, but how can you be an environmental department and then break these products? We do it with one and we do it for science. But so this is as much as you can take apart the Fairphone to repair it. So this is not enough. What we do, and I brought you this example of, this is the keyboard of a framework laptop. What we do is we really try to separate the components as much as possible by materials. So here you can see there's like some plastic parts, there's some metal parts, there's a flex PCB. And then we try to kind of categorize them into these individual materials or material blocks, and then weigh them and assess them. And that's really cool for components that are made up out of one single material. So for example, the plastic casing that you also mentioned, it's great for that. You take it off, you weigh it, you can put a check mark there. Perfect. But unfortunately, this is really inconvenient for populated PCBs. And unfortunately, this is like the biggest part of the impact of these consumer electronic products like the smartphone that we look at. So we have to think of a different way to do that, especially because the ICs that are on these PCBs, they are really the most interesting thing to us. And David will in a second tell you how we do that. But for now, let's just assume we have conducted, like we've taken it apart, we have now information on all the components, we have information on the energy that we need to produce or to assemble the phone, and we have all this data. Then when we move on, we kind of rebuild the life cycle of the phone in a modeling software. And the one we use is really the most humble of them all, and it has the most humble name because it's called Sphera LCA for Experts, which is us. It used to have a different name. They rebranded it to make us feel better. I don't know. So if you want to become an LCA expert, this is your software. But yeah, basically, it doesn't have the nicest graphical interface, but this is what we kind of end up with. So this is kind of the transition that's happening. I also brought this to you a bit larger. So this is the production. The production part of the Fairphone 5, and there's all these other like steps going into this. And I brought one example. That's the battery cover, which is, as I said, one of these examples of having a single material component, and this is mainly made up of recycled polycarbonate. But as you can see, there's also some other chemicals going into it, and there's, for example, this is like the pigment that is being used to color the part. So even though it is like a single material component, there's still some other things that are going into it. And then I also have the assembly process as an example. So here you can see there's the energy going into assembling the smartphone. So this is data we get from the manufacturer. But then there's also like the cleaning cloth and the cleaning chemicals going into this. And so as you can imagine, in total, this is like quite a complex system. And basically, we also want to show you the underlying mechanism of these databases, and this is where David's going to take over from me. Thank you. You're welcome.
One sec. Oh no, okay. I thought I was muted. Perfect. Yeah, so yeah, here's where I take over basically. So what we want to show you now is basically what's behind these little like building blocks that you saw in the software. So actually, in the end, as someone already mentioned in the back, what you want to have for the modeling of the life cycle inventory is like a huge input-output table. Ultimately. So what you're interested in is actually going component per component and modeling really all what happens from the moment that you extract the raw materials from wherever they are, all the different processing steps that happen along the way until you have the component that will ultimately end up in the product. And for that, of course, you need, for every step of the way, you're going to need auxiliary materials, you're going to need energy, you're going to need also intermediate transport to take intermediate products from one way to the other, and even infrastructure. And so what these like kind of building blocks try to capture is precisely all this effort, all these inputs, all these outputs. So as you can imagine, that's actually ends up being fairly complicated. To have that for every component, but then also for the product itself, let alone what happens later on in the life. Which means that, as Saga already sort of mentioned before, actually, we don't do that ourselves completely. So in practice, what you end up having is something more or less like this. So as much as possible, you try to find the so-called data sets for each of the components and or materials that are in the product in these like commercial or even sometimes public databases, mostly commercial, and which themselves already include the full modeling of the production of that specific component on material. Sometimes, however, you won't find, let's say, a data set for the full component, in which case it's something more or less like what you see on the bottom left. You'll basically use these like generic ready-made data sets to model maybe the materials that the component is made of, and then you put yourself the rest, pulling data from either directly manufacturers, literature, whatever it is. Sometimes, however, as you can see in the top left, sometimes you just don't find anything at all. And that just remains basically blank in the model. Exactly. Then you need to model, once you have all the components reflected from the bill of materials, you still need to model the effort that it takes to put everything together. And that will lead you to the product completing, let's say, the model that you build from the production phase. So yeah, just to maybe hammer it home a little bit, because we believe that this is something that many people maybe don't fully grasp about life cycle assessments, is that because of what we just explained, in the end, when you end up having is basically what it's actually product specific data tends to be rather the bill of materials, so what's in the product in terms of material and components, but then how all these things are produced is usually mostly covered by generic data, industry averages, and so on. So they do not necessarily reflect how that particular gold in your phone was actually produced, but rather how it's usually done in industry. And the same can be said for whatever happens rather downstream in the life of the product. So once the product leaves the manufacturer's control, let's say, then you can only basically assume or let's say estimate what will happen with it in terms of how it's going to be used, how it's going to be disposed of. So in the end, you have this kind of like a bunch of generic industry average data adapted to a specific product that you're doing. Yeah. Oh, that's the title is in German. Well, you probably can get it. So basically, so this is a bit what you do when you actually build the model. So going back, Saga before mentioned that actually to gather all the data, you need to actually build or adapt this model to the product you're analyzing. We basically crack open the devices, see what's there, wait what we can wait. But of course, that's not really possible for PCBs. For once, because desoldering every single component is very labor intensive. You can damage the components, and in the end, they weigh so little. And this is, of course, a bit of a challenge, because actually, as we shall see a bit later, integrated circuits and PCBs are actually, from an environmental standpoint, the most important elements in electronic devices. So you actually need to gather the relevant data there one way or another. So, starting with ICs, So what's important with ICs? So the first, so basically what you need to know for ICs is the area of silicon inside and the amount of layers of silicon that you have inside. Long story short, basically manufacturing ICs is a very energy intensive process. There is even some direct emission of global warming gases during some of these steps. So they are very relevant in that sense. And they're manufactured basically in these rather flat wafers that contain many integrated circuits, which in practice means that the bigger each individual circuit is, the more of the impacts of the wafer will be allocated to each of them. So in that sense, you really want to know the area of silicon that you have inside. And in order to determine that, of course, you cannot just do it by just looking at the PCB and the chips on top, because they're trapped in this like plastic housing. So what we do is a couple of things. So for once, we do X-rays, where basically you get to see something like that. So unfortunately, the silicon itself is not directly visible through the X-rays, but what we try to do is basically, since you can't see the contacts, of one, the contacts to the PCB, let's say, of the package, but also internal contacts that there may be where you have some like gold wiring and so on. You can try to estimate more or less then what are the area or the areas of the different circuit dies that you have inside. But of course, that only answers one of the questions. The other question is, okay, what's the area from the top we know, but how many dies I actually have inside? This is especially relevant for complex ICs like memories, processors. Memories usually stack different dies to have more capacity. Processors become more powerful by adding maybe some small memory inside, some controller unit. So what we do there is basically grinding. And when you grind, you get to see stuff like this. So basically, you take a cross section, you cut a cross section of the chip, and you get to see how many layers you actually have stacked. And in the end, this data is important because, again, when you are searching in these like commercial databases to find the data set that better reflects your chip, when you want to scale it and say, okay, how much of this I have in my product, you actually need to know this. So how much area of silicon you have inside, because that's going to be driving most of the manufacturing impacts. And for PCBs, it's a similar thing. So starting from the back, for PCBs, the layers are also important. You had a question? Okay. Yeah, the layers are also important because basically PCBs have this like copper pre-preg layers, which of course will have an impact on then how many manufacturing steps you're going to need, which will make them will have higher environmental impact. So you want to know how many layers you have. With PCBs, normally this data point is actually known, so we don't usually do grinding for them. It's usually not necessary, but in case of necessity, it can also be done. And you can more or less try to estimate from how the cross-section looks, how many layers you actually have inside. But also the area is important. Maybe rather more so than the mass, because similarly to ICs, the PCBs are also produced in in layers like this that are fairly flat, and rather than the impact is allocated based on the area they cover from the full layout. And of course, in cases like this, also waste is important because, as you can see, this example, I don't remember. Do you remember what product this is from? Well, is a Fairphone mainboard, exactly. So basically, as you can see, yeah, it's there. I'm a bit stupid. Yeah, so basically, as you can see, it's produced in like fours with some additional material. So of course, you don't want only to include in your model how much ends up in the product, but also how much you lose along the way. So in that sense, layouts, pictures or drawings like this tend to be fairly useful when deciding how to scale this. And the last thing to be said about the production and let's say like rebuilding the product is maybe something a bit disconnected from what I just said, but it is very important. The energy mix. This is a bit tricky because, of course, as I mentioned, you're going to be working with commercial databases and ready-made industry average data sets most of the time. So it's not always the case that you can actually adapt this to the actual location of the production of your product in particular, or the product that you are analyzing. But as you can see, if you can, is important to do so. So here in this graphic, basically you can see a spread of the global warming potential of manufacturing 1 square meter of PCB for different layer counts, let's say. And then the different colors represent different energy mixes that you have actually in the production site. The red one being the Chinese electricity mix, the green one being the German one, and then the blue one, it's basically only renewable energies. As you can see, the difference is already double for the, let's say, the lower side of the graph. It becomes even somewhat above 4 times more just for producing the same product, same amount, depending on where you do it. So as I said, unfortunately, it's not always the case that you can actually manually adapt this in these commercial data sets, but if you can, it's important to do so. And with that, we've explained more or less what the production phase entails in terms of manufacturing, in terms of modeling and whatnot. Moving on to transport. Transport is fairly simple, let's say. Basically, here you want to cover, especially if we're talking about product level. Here you want to cover basically the main transport. So what it, the effort it takes to move all the components to the place where they are put together. The effort then that it takes to take the whole product into the stock or the hub where it's going to be stored, and finally the effort that it takes to take it to the consumers. The important parameters here, and this is usually stuff that manufacturers have a fair good knowledge about because they tend to know where their products are going and how. But here the important parameters that you want to take a look at is basically the means of transport. So how it's taken is done by air, is done by land, is that by sea, because that's going to tell you, of course, then in the modeling behind it tells how many fuel that uses, what kind of fuel, how much it burns, and how much it emits basically during the transport. Then you want to know the distances, of course, because the longer the distance, the more fuel you're burning. But also, and here you can either do, depending on, again, goals of the study, the kind of questions you're trying to answer, you can either go for a specific case of taking a product to a specific point A or B, or for example, in our case for the Fairphone, we tried to cover, let's say, or the whole set of sales they have and places they ship their product. So we rather did this kind of like a weighted average of distances based on the sales split. And finally, usually the effort for transport is scaled based on the mass of whatever you're transporting. So that's kind of like the last bit of information that you want to know for modeling the transport phase. Then moving on to the use phase. This one varies greatly, not only because, of course, each product will end up being used differently, but also because it depends a lot on which kind of product are you actually analyzing. So, for instance, if you were looking at a washing machine, for example, then it's not only important basically the electricity that you're using, but maybe you also want to take a look into or include in the model the cleaning agents that you're using, maybe in any maintenance work that it may need. So here it depends a lot on the product, and it also depends a lot on your functional units / research questions. So this here, it can be many things. In the case of a smartphone, however, it's again fairly simple. Our functional unit was basically the use of the smartphone and accessories for 3 years for like a regular user. So in our case, really, use phase boils down to just energy use of the phone. So here the key the key aspect once again is the energy mix that you use to model that that energy use and its impacts, because as you saw before, and as you can see here also, it can have a great influence in the results that you end up seeing. In our case, for the Fairphone, for example, similar like what we did in the transport, we basically take a mix like the division of sales that they have per country, and we create a specific energy mix with the weighted average of all these carbon intensities and energy mixes and so on. And from there, we finally move to basically disposal or end of life. here, once again, a similar thing. And remember also this graphic that we showed before, saying that the further down you go into the life cycle of the product, the more generic data and the more like diffuse data you're using. And this is particularly true for the disposal, because in the end, it's difficult to know what happens to every phone in the end of its life. So here we work, yeah, exactly. So there can be many options that could happen to it. Many phones are actually kept, so they don't really have an end of life per se, or at least they have it one very later on. Many of them are discarded, but then some of them, may be recycled partially or totally. So in that sense, one thing that we try to do is basically try to look at the statistics. What's a plausible generic scenario that we can expect for the device to have? But of course, once again, repeating this a lot because it's fairly important, depends a lot on the goal of your LCA. Whatever questions you want to answer. So if it's important to you to know actually what the benefits of recycling are, then maybe you don't want to have like this generic case of what's the most likely thing to happen for a phone, but rather you specifically want to look at what happens if you actually recycle it. A key aspect of modeling end of life is that it comes with a great deal of uncertainty. For first of all, for what I've been already saying, that it can have many different end of life paths, but also because for this particular life cycle stage, the data is incredibly scarce. Also, for many of the commercial databases, the datasets tend to be even rather outdated. So again, here is the life cycle phase that has probably the most like holes in uncertainty when it comes to the data you're using. And maybe another important point here to keep in mind in this, especially if you have recycling, then allocation becomes an important question. Because if part of your product will be, some effort will be put into taking it out of your product and eventually into another product, then very quickly you have the question, okay, who's to blame for the additional environmental impacts of this process, or who's to be credited by the benefits? Is it this product? Is it the next one? So here again, a lot of methodological questions to answer, also depending on what you actually want to find out. Yeah, and with that, we've covered basically the second step of the lifecycle assessment, which is inventory. So gathering all this data, reproducing it in the model. Now we get to the impact assessment. So the impact assessment, as I already mentioned it a bit before, it's where you take all this basically huge input-output table that is the lifecycle inventory, and using different mathematical models, depending on the impact categories that you're actually interested in, you transform that into the indicators. That always means, so as you said, so for example, for global warming potential, you'll basically want to be looking at all the greenhouse gases that are emitted throughout the whole life cycle according to the inventory that you build, and then transfer them into these kilos of CO2 equivalent. But other indicators then kind of pick up other different flows throughout your inventory and then transform it into the environmental impacts that you will analyzing. Usually, I mean, you can go very deep into the different models. Some of them tend to be very complex. They involve a lot of especially for ecotoxicity, for example, a lot of biology, environmental sciences, and so on. Fortunately for us, usually these commercial softwares do it automatically, so we just press a button and see the results. Usually, you usually have to go deeper when something goes wrong or the results are a bit funny, and then you want to find out what happened. But usually, this is something that is done automatically. And with that, we move to actually the last part, which is the interpretation of the results. Interpretation is again a very wide word, but what you do here is basically look at these environmental indicators that you're analyzing and do certain things. So, for example, a so-called contribution analysis or the environmental hotspots, which is basically seeing, okay, from the whole life cycle phases or even the different parts of the product, which is contributing the most to the different environmental indicators. and why? Where can we trace this environmental impact? What's important? Or you can do a sensitivity analysis, which means that wherever you detect uncertainty or whatever you had when you were building the lifecycle inventory, maybe you had different options. Let's say, for example, in end of life, different things can happen. So here you can actually go back, remodel, and see how that affects quantitatively to the results to get a better idea of what your uncertainty levels are, or even check different scenarios to get an idea where the results may move if some pieces are changed. And as you can see in this diagram, it's basically covering and connected with all the other life cycle, like the other steps of the life cycle assessment. And this is before, again, depending on what you find out in the interpretation and what your initial goals were, you may well want to go back to every single one of the latest steps, of the earlier steps, and basically change things. So for the sensitivity, you may want to model things somewhat differently. Or maybe it turns out that the data quality is not sufficient to answer the questions you wanted to, and you need to go all the way back to the goal and scope and change things there. Maybe ask a different question, maybe give a question up, maybe add a new one, etc. So in that sense, the interpretation involves a lot of like moving back and forth until you basically get what you were looking for. In that sense, I'm going to now show briefly a couple of what the results of the Fairphone 5 actually looked like, and a couple of things that we can learn from there. I will not go a lot into detail because a part of what you will be doing tomorrow in the morning workshop is actually reading and trying to make improvement decisions based on the results. So I don't want to spoil too much. But suffice to say, just to get a little sort of glimpse, this covers all the impact categories that we were looking at in the study, but you don't need to focus in them in particular, rather the bigger picture. This is the contribution analysis for the full life cycle divided in the different life cycle phases. So that of course, the first thing that can be noticed is that the production phase is driving massively most of the impacts, from 60% sometimes to even almost 100% in other indicators. This is actually fairly common, a fairly common result for electronic devices, because they tend to be fairly energy intensive to produce. It goes a lot into actually making them, and especially for products like phones, where the lifespan tends not to be too long. They're not very energy intensive when you use them. Then you basically see that most of the environmental impacts that they cause is when they're made, and not really so much after. In other kinds of products, like for instance, servers, even lamps, you actually see the opposite. They usually live long. Sometimes in the case of servers, they even use a fair amount of energy during their lifetime. So the most of the damage, let's say, happens when they're used and not comparatively when they're made. So zooming in the production, here you can see also the contribution analysis now per module. This is only the phone. This doesn't have the accessories really. It's only the phone. And what we can see already is that basically the main board has a significantly higher contribution than everything else. The display is also kind of up there. And then to a lesser extent, the 3 cameras that the phone has also have some contribution. All the rest has almost a negligible contribution in comparison. And if we zoom in, as we mentioned before, actually this is mostly responsibility of the production of the integrated circuits themselves, and in a minor sense also the PCB. Again, this is typical for this kind of devices where you have a rather small PCB very densely populated with chips on both sides. So you'll see something like this, that actually most of the environmental impacts are driven by the manufacturing of that electronic that is in the phone. Most of the rest has comparatively low impact. Even the cameras that you can see there, the impact of the cameras is also coming from the little CMOS image sensor they have inside, so another chip. Yeah, so this is just a picture. Tomorrow there will be, yeah. For the display, there we had actually, there was, if I'm not mistaken, there was, I think it was a polarizer, wasn't it? It was a polarizer that goes onto during the manufacturing of the display. But there, and here we come to the whole commercial datasets thing. Here it wasn't fully clear. It was actually reflective of the actual technology, because Fairphone changed from in the Fairphone 4 to the Fairphone 5. They changed from LCD to OLED, and there was no dataset for like ready-made for the OLED, so we built it our own. We knew the materials. We finally, in the end, got access to the energy that it takes to manufacture it from the suppliers. But to model the polarizer, we used a rather outdated old dataset, so it's still not fully clear if actually the actual polarizer that you need for OLED displays has such a high ecotoxicity impact, or this is just the data that we had to use that is fairly outdated. But that's where that was coming from. Yeah. Yeah, so more of that tomorrow. But just to maybe wrap it up a bit when it comes to the whole life cycle assessment, I would like to talk a bit about the limitations and uncertainties. I think this question was a good segue as to the challenges. So, well, a practical issue, not necessarily always there, is that, of course, a fair amount of prior knowledge on the product is needed, apart from the methodological knowledge, and these two are not necessarily always there. But I think the most important, let's say, problem or challenge with LCA is data. So, as you have seen already, building a lifecycle assessment takes a huge amount of data that you need, and it's very data sensitive. For example, one of the things that it has is this weird thing where the more you know, the worse it is. Because of course all the data points that you don't know end up not being in the model and somehow make the results look better. So actually, if you have very extensive deep knowledge of your product, your result will probably be worse. More reliable, but worse. So, and then of course, it's very often the case that data is either outdated because these commercial databases, well, they don't have the capacity to update all their data sets every year. So in the end, and some technologies do actually advance fairly fast. So you'll be working with a lot of slightly or very outdated data, and sometimes completely missing. And there you have to find a workaround, maybe try sensitivity analysis to try to quantify, okay, what's going on. Or what the effect of this uncertainty may be in my results. But ultimately, the best way to deal with this is transparency. So transparent reporting in LCA is crucial so that whoever ends up using the data that you're producing, the results you're producing, knows better how you did it and to what extent they are reliable, to what extent they can be used for certain things and not for others. And in that sense, transparent reporting becomes fairly relevant. And with that, I'm done with basically explaining what the LCA is. Yes?
Okay, I have a few questions. Maybe the first,
Yeah.
I think the repairability of the Fairphone is one of the main benefits. Did you consider it doing this life cycle, especially with the functional unit of 3 years?
Yes. So in the study, then we had let's say some scenario analysis when we were building alternative scenarios and seeing how they compare, and one of them were actually repaired. So basically saying, okay, if some repair is undertaken depending on the module and the lifespan is extended longer, what is the benefit when compared to a scenario where no repair is undertaken and then you need to get another phone? We didn't get into that today because that may be one of the questions to be answered tomorrow. So yeah, more on that tomorrow.
And then the other question, what was the purpose of the LCA?
So they have actually, in the case of the Fairphone 5, they have several. So the goals they had, I mean, the first one is just to monitor the environmental impacts of their products. They also communicated. They usually publish the whole report. So it has some marketing aspect to it in the sense of like communicating, but they're in their sense they're also, I mean, in one of the first slides you had the evolution of the different designs. So what Fairphone actually does fairly well, in my opinion, is try to feed back the results of the LCA in the design. A good example, I think, is in one of the earlier versions. The display was connected to the main board through a very big gold-plated pogo pin connector. It had like a significant impact compared with the other connectors, especially considering that if your phone is not modular, you don't need that. In the newer models, they already changed that to a very regular, like board-to-board flip connector. So in that sense, they also use it for like a bit like eco-design. And another explicit goal they had was to actually see, okay, not only what they can improve in the design, but also where they can like engage with the suppliers, basically. So if for example, the chips have a high impact, maybe they try to talk with the suppliers and see if they can use renewable energies, etc., etc. So a bit that.
And then for like looking at marketing or communication, wouldn't it be more interesting to do like comparable lifecycle assessment? Because now it's really hard to evaluate the results. Like comparing it to other phones, it would be more interesting because right now my takeaway is like the circuit is I think one of the most important parts. And are they really doing the things differently with the circuits? Like this things would be interesting. But they decided against that comparable life cycle assessment.
So I agree. A comparative LCA is always more interesting, but it's also more challenging. And for example, the ISOs 14040 and 14044 require that if you do a comparative LCA, then this has to be reviewed by an independent panel, which of course is great because it ensures certain reliability, or at least there is someone else that is checking that you're doing everything as correctly as possible. But in practice means that it needs more time, more money. And also an important aspect is that Fairphone has a lot of data about themselves, but they don't necessarily know how others do their stuff. So actually, for a proper, reliable comparative LCA between two models, you either have the two companies on board, or you have, let's say, as little data of both as possible. But yeah, if Fairphone could come to us asking for a comparative LCA, it would be difficult to make justice to the other device for which we don't have the data. Okay, you first.
Are there any ways to are there any ways to calculate the level of uncertainty inside the LCA?
There is some ways. So, for example, something that some LCA studies do is Monte Carlo analysis. I'm personally not very familiar with the whole procedure, but I know that certain softwares, like I think OpenLCA of all softwares, has a pretty good tool for this Monte Carlo analysis. So basically, that tries to a bit, through simulations, try to get okay. If you add up all the uncertainties that are known to the datasets and the ones that you as the user put in from all the modeling, the decisions that you took in the beginning, it tries to quantify. But at least as we do it more like just not so quantitative, but rather qualitative, by looking at sensitivity analysis, different scenarios where we know that there is uncertainty in different cases, we just look at it.
Okay, but are the results concrete values or more just like ranges of the values?
I would say rather ranges.
Okay.
Again, going back a bit to the slides before, you're working with mostly generic industry average data. Every single data set is its own little LCA module with its own uncertainty. So in the end, the specific numbers are very likely always subjected to very high uncertainty. So you're always working with ranges or orientation, let's say.
Okay, thank you.
Yeah.
Okay, sorry.
Sorry.
I have two questions because I'm not really sure and I'm interested. Is the customer itself or himself part of the LCA? Like the customer side?
You mean the customer of, for example, the users of the device?
Yeah.
Yeah, so of course, when you model the use phase, you can take them into account to a certain extent. So like because in order to not introduce too much noise, we decided to model the use phase just based on amount of charges done per day or for a normal user, try to get a feel of how many this would be. um, based on available data, but you can even go deeper and say, okay, what do users do more with their phones? How much they're actually using it, and how that's translate into the energy. Yeah.
Yeah, because that's quite interesting for me because I mean it's extremely cool that you can construct and configure those quite perfect LCAs, but in the end, the customer, okay, not perfect either. So yeah, obviously, but in the end, the customer, um, I don't know if everyone is likely to actually repair their Fairphones. I mean, I have some friends of mine. They bought those Fairphones, but 5 or 3 years later, they decided to buy another more. I don't know what's the word. Yeah, they switch the brand,
Yeah.
or they leave the common sense of Fairphone. So I think that's an interesting part of all of this. Yeah.
Absolutely. Again, in the end, all well, Sarah, if you wanna.
That's always the issue. Okay. Well, that's always the issue you have, that actually, you know, with an LCA, you just do this, like, you try with the statistics you have to make the most accurate generic result. But obviously, what the individual person does is it highly affects not just for the use phase, but also, for example, for the disposal. I mean, you have people who throw their electronics in like household trash. And obviously, the life cycle assessment of their specific phone is going to look super different to a person who disposes of it properly. And this is kind of this uncertainty that we never get out. So it's also kind of what we tried, or what I meant when I said that on the slide where we had the research questions, we had this. When is repairability beneficial, under which conditions? And it is exactly that. It's you need to actually use your phone for longer for the additional effort to kind of even out later on. But there is no way yet. I mean, it's getting quicker and quicker to conduct LCAs with automatization, but there's no way yet of doing like personal LCAs. But it's a very good point. And you had another question, right? Okay.
You also had one?
Yeah.
Okay, and then you, or well.
Okay. Yeah. So following to that question, like repairability, like just as she said, like some of them switched to another brand. So
Yes.
I don't think they switched because of like it was broken or it need to be repaired. But if it was upgradable, then it might be like more like it will significantly increase the lifespan of the phone compared to repairability. So, do you also consider like upgradability in the LCA?
Not in this one, because well, Fairphone themselves so far haven't come to us with the question. So I don't know if they're working on it, but so far, at least for the Fairphone 5, they weren't still implementing it. That I guess also is a technical question, to what extent it's easy or possible to design a device to be upgradable. But of course, it would be interesting. Yeah, go for it.
So, but what they have done is a camera upgrade for one of the older
Yes.
Fairphones. So that was the only one where they really had a new hardware development, which was an upgrade. But what they haven't done, what he said, well, they haven't really done it so far, is the mainboard upgrade, which is the main obstacle. But also you can, of course, upgrade memory and stuff like that. So it's also some of the issues which might deteriorate your experience with your phone, which is why you leave it. Some of them you can upgrade, but the core thing, the main board, which is also the main environmental impact, you can't.
Okay.
That's still the point.
And is there any points for upgradability in an ISO standard for LCA? Like, if
No,
they
I
make
mean,
it,
you have to build your model more complex to cover
Okay.
that, because you basically have to look one generation in advance, and you would have to have a fairly specific technical description of what the replacement mainboard will look like, which is in the future, and you don't know it yet, right?
Yeah.
So you can make models like that, but it's getting more and more complicated. And
Okay.
it's on one hand, there's so much better experience in doing the LCAs over the last 10 years, and also data situation is vastly improved. And nevertheless, everything that he said, there's sometimes black boxes, no data at all is still true. So it's both. It's been getting a lot better, but for these more complex models, there are still too many gaps. So we would like to do them, but it's too much work.
Okay.
So you're doing thank you. So you're doing LCA when the product is in the market, right? When you have the data of the use case. But my question is, if, for example, we saw an impact of IC, how much it is impacting. If you incorporate this in the design level or in the prototype level, at least for the in the IC manufacturing or something, when the manufacturer or the company comes with the design of the product, consider an IC with some process or something, you can actually is there a chance that you can give your assessment saying, if you come up with this design, there is this wastage of particular parts in the board, or the IC or the processor is taking more power, you can actually come up with a processor which consumes less power, or maybe to be in the micro level, maybe like there is something called a dark silicon where you can't turn all the parts of a processor completely on, so you can still give some steps or some other alternatives in the pre-production level, so it would be much more helpful to incorporate than in the after the production level. Is there a chance to incorporate LCAs in the pre-production level also?
Yes, absolutely. It's also done. We're both also involved in European research projects where actually that's the point. There are certain technologies that are developed, and then us as LCA practitioners, we're there to kind of follow up the process, and during the design phase going like, maybe this alternative would be better, or this is showing a high impact here. In the case of Fairphone, it's more that several stakeholders, I think they basically, when the product comes out, they actually want the carbon footprint of that product. So for them, it makes more sense to do it when the product is done, so that they can use already that number to communicate to the stakeholders that ask for it. And then in their case, the eco-design improvements tend to come rather in the next iteration. But of course, if your focus is really trying to improve your product, it makes more sense to incorporate the LCA already, and it's done. So yeah, sorry, you can catch us later, but it's getting late, and still we have another section that Nils will present. But yeah, we'll be around. So the following questions, just catch us around.
Although it's always difficult, because maybe the questions are actually more interesting than what I have. I have two short sections only for the end of today. So one is eco-design. It's, oh, did I get the, no, it's not the last slide, but whatever, small changes are missing. But I'm not talking about the eco-design of the Fairphone or of a specific product, because you will be doing some part of that tomorrow in the exercise. And just to stress a bit more, like what David said, you will not do an LCA of the Fairphone, obviously, tomorrow, because that can be done in 90 minutes. You will be using the results we already have and then discussing about options with a smartphone more in general. Whereas I'm more looking at now design strategies for larger systems. So not a single smartphone, but rather the entirety of all the smartphones, or the communications network that makes your smartphone work. And that's actually where there are some differences in how you approach the LCA to do these very large scale analysis. So for these design strategies that you want to come up with, it's definitely a big difference if it's single product or many products together, if it's also the complexity of the system, or like you said just now, if you want to do design changes, how complex are the design changes? Even just exchanging one material somewhere in the upstream might have consequences in the rest of the life cycle, and you can't just keep the same LCA model for all the other steps, but you might have to make changes because of only exchanging one material. Sometimes, of course, it's just exchanging one material for the other and the rest of the model doesn't care. That's the simple case, but it's not always true. So the complexity of the changes can also be very different, and then multiply that with the complexity of the system you're analyzing. Then the company type, is it a small or large company? usually shouldn't make so much of a difference, but actually it does, because what the company can influence is very different. And what was not mentioned before is that, I mean, you saw that there's the energy mix of China. So the Fairphones are actually manufactured in China. It's not like the small company Fairphone suddenly can produce smartphones in the Netherlands. So, but they selected suppliers in China where they think they have higher standards and higher wages, definitely, so than the other Chinese manufacturers. And that's the process they went through with the Fairphone 1 and 2. And since then, they've got very stable supplier relations there. Okay, so I'll skip through a bit more of that, but where we need the more complex system analysis models is, like I just mentioned, for the communication networks. And that includes, and that's also why I'm presenting this next part, that also includes sensor networks, which some of you will be having as an example in the large exercise. But also for data centers, high performance computing, cloud data centers, now AI-enabled data centers. For all of these, it's not just like, this is one product, but this is a whole range of products which work together to then produce the capability of a cloud data center, right? So it's not a single product LCA anymore, it's a system of many products together. And just very shortly, without the details, where we developed this actually is we did a study for the Environmental Protection Agency, the Umweltbundesamt, on the development of our mobile communication networks in Germany. For all of Germany, what's the environmental impact or the energy consumption, first of all, and then the carbon footprint of the mobile communication networks in 2030? And that is not a product LCA. So there we had to find other ways how to structure especially the inventory phase of the LCA part. And I'm not going to go through all of that, but what you see here is the frequency ranges. No, again, I have the same problem that Sarah had before. So the frequency ranges that the different parts of the network operate in parallel. And these different categories here are from industry areas to inner city areas, and then to rural areas, which have a totally different mix of the frequencies that are in use because of the reach of the bandwidth in the mobile phone networks. So that means we had to model some of frequencies that were not even used at the time when we did the study, so they were future technologies, and we had to see how the development of bandwidth and number of subscribers and so on in the different areas within Germany are distributed, and then you can calculate it for all of Germany. So again, not enough time to go into more details, just as an example. So what we came up with in the modeling is what we call the 5C method. And the 5 C's are in the front here, so capacity, condition, configuration, component, and control. Very nicely done with C. And I'll just switch to this one. So it can also be done in German with 5K. So we do have both publications in German and in English, and then it's either 5K or 5C. But for today in English, so it's 5C. And what we do here, the standard product LCA is mostly kind of covered here in the component part. So it's like, what is the hardware really consisting of? Which materials and how are they produced? So that's a bit similar to, or mostly similar to what you heard before. But what you then need, especially for a router in the network or for a server in a data center, is the configuration. So the product type, like this is a server from this brand and has this name, doesn't even tell you how much memory is in there, how many processors are in there, how many ports of a specific speed are in there. So configuration is vastly different if you look at these large system analysis than compared to a single product. And what we actually then have as the functional unit, we have the capacity. So in the network sense, it's the carrying capacity of data or communications in total. But with the sensor networks that you will be doing in one of the examples, actually, you don't use all of the network. There's a network already installed, and you only use a few % of that network with your sensor data, because hopefully your sensor has very little data to transmit, right? So again, capacity then doesn't mean the whole transmission capacity of the network. It means what part or what percentage of the actual large system that somebody else hopefully has analyzed for you, how much of that are you using with your sensor data, right? So that's the capacity part in this case. And then the condition is, well, how is the system set up? Is it kind of point-to-point, or is it a star or a configuration in the network? What's the frequency, the bandwidth, and so on? So those are the kind of things that the person or the company actually operating the network can still choose. So you have the same hardware, so it looks like the LCA is the same, but you can choose different operating conditions and you will have a different LCA result at a different capacity, obviously. And similar then, control means stuff or single control points that the company who's operating the network can still change by using the same hardware, but having totally different results. Like using renewable energy is a choice you can make, and it will change your whole calculation, but it's actually not changing what is computed or what's transmitted. So the hardware seems to be exactly the same, but you have parts where by control, or also by having software, like especially power management software, where the same hardware can be operated in a totally different energy efficient or non-efficient way. So these are just as a short overview. You will not use the method as such totally in the exercise, but as background that you have heard what the 5C method is. And I just, this just ordered differently, same method. And again, just showing that this is kind of the range of the eco-design options you are asking yourself or your customer is asking. It's on one hand, it's more like on the production phase, and we heard that for smartphones, production is most important. For sensors, we have a different story, of course. So production is also important, but actually the system that the sensor is controlling is actually even more important. So you might have heard that story maybe already yesterday in the introduction, otherwise it will be later today. But then you also have things which are not defined by the hardware you design and put into the field, but which are software related or user related or choices. So that's the range where you have to find for your eco-design options. Am I concentrating on exchanging one material, and is that actually changing the whole life cycle of a communication network? Or do I have to use a better power management, like shutting down high frequency links in the night because nobody's transmitting data and there's an alternate route which is still available at night, stuff like that. So that's power management on a large scale. And that's being done, but there can be much more can be done there. Okay, and the final slide for that part is, you've seen that before. So having all the single processes which lead up to the product LCA, and just to stress it again, one product? No. If you look at systems, then suddenly you have many products and they are interlinked, and whether you need one server or 3 servers to achieve the capacity that you have for your application, of course, you have to model all these interactions between bandwidth, computing speed, and memory requirements, and so on. And that's why we came up with this method to have a better inventory of these large complex systems. Not for a single product LCA, you wouldn't need that. But for the large complex systems, that's why we came up with that. All right, and then last part I have is slightly different, something slightly different. So jumping into where can you get data? And you might use that in some of the example calculations, but as I said, for the smartphone LCA, you will not look for additional data tomorrow. I don't think so. But so there's by the Environmental Protection Agency, Umweltbundesamt, they have a public German database, and so we will just kind of give you an introduction to that in 3 slides. They have been developing this database for a long time, and it's always been fully public, and they've upgraded it recently, so it's a bit more user-friendly, but also a bit more separating between generic data sets and the more specific data sets, which might, if you go deep down, you might need those data sets, but they will not help you for doing a rough LCA in a quick way. So that's yeah, so the data set actually is called Probus, it's now grown a lot, 23,000 data sets, which again, for electronics, that's never enough, right? In the commercial database, a few years back, they had 100 different electronic components, and it sounds a lot, but 100 is nothing if you have different types of products in front of you. So again, 23,000, much of that is like base materials, and then base materials like copper with recycled input or without copper recycled input and stuff like that. So that's already a large portion of that. But then it's also quite specialized, and also including some electronic data sets, some of which we have actually either upgraded or provided for the database as well. Yeah, and here it says, yeah, so it's been updated in 2024, which was a good thing. It was a bit really old-fashioned and not very user-friendly to find any of the data sets. Especially what's important for the data sets, and that comes back to commercial databases like Sphera that we mainly use, is the data quality part. So the documentation of the data, once you find a data set and it sounds like you have what you have in your product, then it's really, you need good documentation to find out whether you can just use the data set or you have to modify the data set, maybe scale it by a factor of 1.2 or 1.5 or whatever. But what's your scaling factor? How do you get that? So that's kind of the work that's actually done then when you do the LCA. It's like looking at the documentation of the data set. Can I use that data set for the component that is in my product? And as I said, 100 electronic component data sets is nothing. We would like to see thousands of them to cover all the different components that are used in electronics. All right, and with that, at the end of the time, oh, overtime already, yeah. Did you warn me? So, I don't, we started, oh yeah, we had technical difficulties, yeah. So maybe we can allow 2 more questions and going into further into the break, just in case. Are there 2 more questions? Otherwise, we'll continue tomorrow morning. As I said in the beginning, we'll be around, the 3 of us, for questions in between as well, in the breaks and so on. And otherwise, we'll continue with the LCA exercise tomorrow morning at 9 o'clock again. So, no questions right now then. Thank you.